Okay, so let us continue our session, and the second speaker is Gang Yang from the Institute of Theoretical Physics of Chinese Academy of Science, and he will talk about bootstrapping of SU3 lattice Yang-Mills theory. Please welcome.
Okay. So thanks for coming, and thanks very much for the invitation to give the opportunity to talk about our recent work. This is based on the paper appeared earlier this year with my students, Yuanhong Guo, Zeyu Li, and Guorui Zhu. So it's a relatively new field or new direction have been involved, and but this whole work has been done, I think, more than 2 years. So finally, some results we can publish. And so please feel free to interrupt if you have any questions. So let's first give you some motivation and background. So in studying physics, normally we may encounter some difficulties. For example, when we're going back to the 1950s, we don't even know what's a fundamental theory to describe strong interactions. So when you don't have a theory, how do you make predictions? Okay. And also, sometimes even you know the theory, it's in the non-perturbative regime, and you don't know how to compute it, because the most well-known methods are perturbative computation. So this is precisely like Park confinement problems. And also, even sometimes you know how to compute it. For example, if you want to compute a 10-loop Feynman diagram computation, in principle, you can draw all Feynman diagrams and sum them together. But practically, this is impossible to do. So in all these kind of cases, it will be helpful to consider alternative strategies that what I mentioned here would be the bootstrap. Basically, you want to consider some physical properties so that you can constrain your final results directly. In this way, you avoid the intermediate, this complexity steps. So, so what is bootstrap? And a picture will show you that to pull yourself up by yourself. And this is a picture from, I think, from the German fairy tale story. And actually, in China, you probably know the Kung Fu. And actually, it's in some martial arts novels, there is a Chinese Kung Fu called Ti Yun Zong. Basically, you step your right foot on your left foot, then left foot on your right foot, you pull yourself up into the sky. So this is a very remarkable Kung Fu you can learn. Of course, this is a kind of a fantasy. Sorry? You mean the Kung Fu? This is, yeah, from the fiction. The fiction, I think, is in the 1960s. But Gulong is a very famous. Yeah, it's a yeah. But the story would happen maybe in the thousands of years ago. Yes. So so of course this is I mean, physically this is impossible, but the idea actually physicists borrowed from that to develop this bootstrap programs. I think the most important one I should emphasize would be back to the Wheeler and Heisenberg, also Jeffrey Chu back to the I think the last century. They want to develop this S-matrix program to study strong interactions before QCD was invented. And also this conformal bootstrap also has a long history, I think back to the 1980s by Polyakov and many others. And more recently, I think in around 2008, Richkoff and collaborators generalized this conformal bootstrap to high dimension CFT. And since then, also there's many other developments like modular bootstrap and EFT bootstrap. Also on the other side, the modern amplitudes on shell method is kind of a renaissance of the old S-matrix program. But there's many developments, not just non-perturbatively, but actually at the perturbative level. You can, but now thanks to these new techniques, you can do quite high loop computations, which was not possible before. And the topic that we will actually use, I will explain, is called the matrix bootstrap framework. It's kind of different from the other strategies. So, and the physical problem we want to focus is non-portable QCD, which is quite the real QCD actually in our mind. So the fundamental theory, the Lagrangian is known, which is actually you have this gluon part and also this the quark part. Okay, and the remarkable property of this theory is that if you consider the RG behavior of the coupling, in the high energy you have this asymptotical freedom, and when you go to the IR region, the coupling you have a strong coupling this dynamics which lead to the confinement. And if you consider the physics, actually this is controlled by this so-called beta function. Beta 0 is just a leading order. It actually contains two parts. One is this given by the fermion loop. The other is a gluon loop. Okay, the fermion loop is actually the same. This minus 4/3 is the same as in QED. The important here is a sign. Okay, in QED, you know the coupling increase when you go to the UV region, and the very crucial point is that in non-abelian gauge theory, you have the gluon self-interaction. So this is really contribute a positive components here. And in the realistic QC theory, the gluon, this term will dominate, which puts beta 0 to be larger than 0, positive number. So this actually gives you this anti-screening effect from gluon. And so, I mean, to study pure Yang-Mills theory in this respect will be already very crucial to understand this confinement mechanism. And of course, to understand the Yang-Mills mass gap problem is one of these millionaire prize problem by Clay Institute. And of course, if you want to win this prize, you have to satisfy certain mathematical criterion. In particular, this is I think from the problem definition by Yeffel and Wheaton, you have to at least as strong, this property at least as strong as these two cited here. Okay, this Whiteman, of course, the famous he has a famous book about this mathematical structure of quantum field theory. Also, this Ostwald-Schreider set some axiom for Euclidean green functions. So actually, there's one very important property, so-called reflection positivity, developed in this paper. We will use this property, plays a crucial role in our study here. So there have been no methods, for example, in some low-dimensional case, we may solve, for example, in 2D QCD, maybe solve them exactly. Also, in certain theories, you have a specific symmetry, for example, like the famous Seiberg-Witten theory, you have a supersymmetry, or you have a conformal symmetry. This would help to solve this kind of a theory. And they also have developed some effective field theory, like chiral theory, heavy quark, or NGL models, etc. However, how to connect the fundamental QCD to this effective theory, this is still, I think, not known. And as we may all know, that the most successful and quantitative method so far is actually the lattice simulation. This is based on the lattice-free formulation of your QCD, and you perform a pure numerical Monte Carlo simulations, and you can compute those numbers to quite high precision. So in this talk, we want to use a different strategy, but so-called positivity matrix bootstrap. We will also consider this on the lattice framework, lattice the QCD framework. Okay. Any questions so far? So this is actually a relatively new field, and it's the strategy was first proposed by Anderson and Krusensky back in 2016, and also later by Vladimir Kazakov and Zhechuan Zheng, I think around 2022. So there are also the similar methods has been applied in some other contexts by Henry Lane in matrix model and Han collaborator like matrix quantum mechanics, as well as Cho in Ising lattice, etc. But still, the application in this for the gauge theory is still a relatively quite new direction. Okay, I think any of them, if you are interested, it may be a problem to I think lots of opening problems still need to develop. Here I would like to highlight several advantages of this strategy. So normally, for example, in the EFT, you guess this effective field theory, and in the conformal bootstrap, you really don't need to know Lagrangian. That's actually the usual bootstrap strategy means. But here, actually, we do need to know the fundamental QCD action. So this is the kind of bootstrap which is kind of different from the other philosophy. Okay, as we will see, this will be theory dependent. The detail of your Lagrangian enter into the construction. And also, it does not ask for specific symmetry. It doesn't ask you to satisfy supersymmetry, conformal symmetry, etc. So this is one of the, I think, the advantage if you really want to deal with realistic series. Also, it's kind of applied to general space-time dimension from 2D, 3D to 4D, which I'll present some results here. And unlike the pure this lattice Monte Carlo simulation, you also need to have really have analytic control for this study. And so here I show some progress we have made along this direction. So previous studies, like in Anderson and Kruzinski, they consider this large N-Yang-Mills theory. And Kazakov and Zheng, they have some concrete results in SU2 Yang-Mills theory. So in both these two theories, the only single trace loop variables are independent. Actually, so it means that in some cases it's very simple. There's no need to consider multi-trace operators. However, if you consider the SU3 case, which is actually more close to the realistic QCD, this first case you need to really deal with both single and double trace operators. And this actually increase the complexity of this construction significantly. If you know why there are only single trace in SU2 or double trace in SU3, there are some trace reduction formulas here. It's not so important in some, you can trust me for this reduction. Yeah, it's a matrix properties. So, and I will explain some techniques later, methods later. Here I just show you the SU3, 2D, and 3D, this plot. So the x-axis would be the coupling. It's from the 0 to 5, really from weak to strong coupling. And the y-axis is about this vacuum expansion value of this single Wilson loop. The most elementary is this plaquette vacuum expansion value. So in the 2D, it's solvable. So you have both analytical results, and also the bootstrap gives you the upper bound and the lower bound almost coincide with these analytical results. And in the 3D, it's no longer solvable, and but we have some weak coupling or strong coupling expansion curves. This red dot would be some Monte Carlo simulation data, and these are the bounds that you can get compute on a laptop. Okay. Next, I will discuss the methods in more details. Okay. So first the setup. So we consider this a pure Yang-Mills theory, so without quark here, and some of you maybe know the lattice formulation. The action is given by a sum over all this plaquette Wilson loop for the full lattice. Okay. This UP would be the single plaquette here, time is conjugate, sum of all of them. And the lambda is the top of the coupling, and n we will treat finite n here. Of course, this is actually a statistics mechanics problem now on this setup. If you take the continuum limit, take this the A to be 0, you actually recover this the Euro trace F square action for the continuous Yang-Mills theory. But in this lattice setup, what you are interested in is a particular function, okay? And the elementary block you need to integrate out are these link variables, okay? So this placket has 4 link variables, okay? Take the trace, it's gauge invariant. And the real physical quantities on this setup would be some operators, vacuum expansion value of the operators, which is mathematically defined in this way. And the basic operator are the Wilson loops, all possible Wilson loops. Okay. So basically, if you know the all vacuum expect value of the Wilson loops, you solve this theory. And you can show that, if you know the results, you should show that this satisfies the error law, which proves the confinement. And also, you can consider the correlator of the loops, and from them, you can extract, for example, the spectrum of the glue balls. Okay, you can, in principle, you can prove the mass gap, show that I think the first excitation state has a gap. Okay. So our goal was to try to compute these quantities in a bootstrap strategy. Okay. So the main strategy was that you needed 2 basic physical constraints. One is this positivity properties together with the Schrödinger-Dyson equation for those loop variables. And using this as a constraint, you can derive the upper bound and the lower bound for this Wilson loop expansion value. Okay, that's the main strategy. The main physical part comes from these 2 constraints. Where are they from? Okay. So any problems so far for this strategy? We're going to. Yeah, this in a strong coupling limit, it's very good. Yeah. So in this this would be some non-perturbative regime. So of course this bound is not the it just you have to make some truncation. So when you increase in principle, I think that's a conjecture. If you increase your constraints, in principle, you can do it with more computational resources. It can be thinner. That's what you observe already for 2D. Yeah, this red line is a weak coupling expansion, perturbative expansion. Yeah, this is a strong coupling expansion. Yeah, so the red line are perturbative in 2 different regimes. Yeah, I just showed that to compare. To be consistent, to show that the bounds are consistent with all available data. No, it's not convergent. They're both weak and strong. Strong coupling convergent, but I think it's it still can be analytical continued to the that's true. Yeah, but it's not any continuation to the weak coupling regime. Yes. This you have at each perturbed order you have a strong coupling. Actually, you can compute analytically the expansion. So this is different from the Euro like X4 strong coupling. It's quite different. Actually, you can just from Schrödinger-Dyson equations you can make answers to. In principle, this gives you a strong coupling series. This dot is from some Monte Carlo simulation. Yeah, Lattice Monte Carlo simulations. Yeah. So actually, I think for Monte Carlo you can also have the for the dots for all regions. That is not. Right. Okay, let me first explain what's the property of this positivity constraints. So there are actually two versions have a different 2 physical origins. One is Hermitian positivity, the other is reflection positivity. Okay. So the Hermitian positivity is actually probably very simple. It's just the operator times its conjugate, which will be a modular square. And in the Euclidean, this path integral is bounded from below, so it had to be positive. Okay, so this is actually a very simple mathematical effect. So, of course, this operator you can take as a linear combination of operator, right? But as a whole, it is still the u times dagger. It's like a u modular square, right? It is still positive. But but you can expand it in terms of the components, linear components, then you get a matrix here. Okay, so the whole series, the sum has to be positive, implies there is a matrix to be semi-definite positive. The matrix elements are given by this one. So this is actually just a definition of what would this mean for the semi-definite positive matrix. Okay, so if this matrix is semi-definite positive, basically you take some sub matrix, the determinant should be positive. That's basically the meaning of this thing. And here, this P can be taken as some paths on the lattice. And when you take this trace PA, PB, you actually sew them together as a loop. Okay. I will show you next page more concrete example here. So the U operator, in this case, I take up a 5 path. Okay. So this will be just as an identity without taking trace. This is a path. These all black dots are located at the origin. Okay, so you have paths in different directions, and also, this is all length 4 paths. Okay, if you take the dagger, it's actually just a reverse direction on the lattice. Okay, so you get the 5 dagger path. So you put this first 5 on the row, the other dagger on this column. You sew them together. The sew them means take the trace and their products. Okay, and of course, if you look at the diagonal part, it must be 1, identity 1, because it's just the same path and then reverse direction. It cancels itself. Okay, but for the other off-diagonal components, you get the non-trivial shape of their loops. Okay. Okay, if you look detail, this one is just sew them together, so it becomes a closed loop. And for the others, this one, you see it's a same direction, so it rotates this placket twice. Okay. So, and in this case, you find there is actually 4 distinguished loops, Wilson loops. You set them as a name as the 4 variables, W1 to W4. You get a matrix. Okay. So this matrix has to be semi-definite positive. And this precisely means that you take the submatrix, and their determinant should be positive. This gives you a constraint on this value of the W. Is this clear? No, here it's real. It's real. Yeah. That's also what you do the computation using the lattice simulation. It's a Hermitian operator in this sense. And it's symmetric in this matrix. It's also important as a SDP definition of the problem. So this is an example for the Hermitian positivity. The other more interesting and actually give you more much more constraining condition is this reflection positivity. It actually was first introduced by Oscar Schreider. They want to define some Euclidean version of QFT, and they want to ask this theory, which property this theory has to satisfy so that it can be mapped to a consistent Minkowski physical QFT. And it turns out this reflection positivity is one crucial property. It actually, when you do the anneal continuation to the Minkowski space, this recovers the unitarity property. This is crucial for that you have a positive norm defined in this Euclidean field theory. And to give you a simple analogy, which is introduced by Lieb, actually you can consider this classical Coulomb energy problem. You divide your 3-dimensional space into 2 parts. Suppose on the one side you have this density distribution of classical charges. On the other side, you have this mirror charge distribution. and you want to compute their interaction energy between this side and the other side, okay? You do this integration. So the dx plus is for this area, x minus is for this area. This will be the Coulomb potential. And you can prove by going to making some Fourier transformation to show that this integral is positive, is positive definite. So this is actually a very preliminary version of this reflection positivity. You have these mirror charges. And similarly, if you consider the lattice, okay, you can divide your lattice into also introduce a mirror plane. In the 2D version, it's a mirror line, right? You have the left-hand side and right-hand side. The U plus is one side, U minus is the other side. So to understand this reflection positivity, you can consider this partition function, and it factorize this partition function in terms of these links U in different regions. Okay. It turns out that you can write the full partition function in terms of U0 part, but the integrand is a modular square. Okay. So I think it should be clear to you now, this integral has to be positive. Okay. So this is a mathematical decomposition. And of course, here is a pure partition. You want to consider some expansion value with some loop inserted. So in this way, you consider O plus part time its mirror, and take the trace here. You should take the trace here. So you have this path, which is this side, and the other side is you take the mirror, x to be minus x, also take a dagger to reverse. And in this way, you can write this vacuum expansion value also similarly in this modular scale form. Okay. So it's a particular requirement that you have to construct this this is O plus times O mirror. Okay. And in this way, you can construct a positive matrix as similar as the Hermitian case. So here you consider the three elements in the row, and the corresponding mirror parts. Okay, you can see this is just a reflection it from the right to the left, but in the same time you make a conjugate so that the direction also flip. Okay, so in this way you obtain a 3x3 matrix which has to be semi-definite positive. So is the idea clear that you use a reflection positivity, you can construct a further matrix? It's different from a Hermitian positivity, but this is actually very crucial to give a very tight constraint. And in this paper, we also consider a new twisted version of reflection positivity. You see, it's not a mirror, certainly, right? It's like a rotate a pie. Okay, so this is what I mean by twist here. Unfortunately, we can only prove it in 2D. So if you consider 2D Yang-Mills theory, it's mathematically rigorous, but beyond 2D, 3D and 4D actually is not true. Our computation is show that. So the reason that you can show that in 2D, because in 2D you have enough degree of freedom for the gauge choice. You can set this U0 to be identity. It's particular you can make a gauge choice to make this to be trivial, so that your path integral can be factorized clearly. But in 3D and 4D, if there's a mirror plane, you cannot set the full plane these links to be identity, so that you lose this property. But in 2D, it's actually very useful. We will see later. So any further questions for this part? Yeah, the only invariant point is origin. Yeah, this I don't know. Yeah, compared to the Euro reflection, that would be just a reverse the sign of one direction. So here is like you have both time and space which is maybe some PT symmetry further here. But in terms of other anomaly, yeah, here you just as an operation here. Yeah. Yeah. Maybe in the 2D case, I will show you that if you don't impose this condition, the convergence is actually quite slow. But once you impose this condition, it's giving much strong constraints. This indeed is this condition is different. At least at this construction level, it's different from the other constraints. So yeah. I think, but in principle, if you don't consider this constraint, maybe you need to go to much higher, much larger size of matrix to see the similar constraints. Maybe you can, see the examples later. So the next ingredients I will show you here is this a Sringh-Dyson equation? Okay. So this is a place where the Lagrangian enters. Okay, usually the different theory will give you different loop equations. Okay, why we need loop equations? Because this kind of loops are not, these loop variables are not really independent with each other. Okay, you have this, for example, the four variables. Actually, they are linear dependent. Okay, so you really want to eliminate as enough number of unindependent these variables. And but the physical origin of the loop equation is quite simple. It's actually just the equation of motion. But here we do it at a partial integral level. So this is normally we say it as a Sringh-Dyson equation. It's a quantum version of the Euler-Lagrangian equation. And when you derive this equation of motion, it's like doing the similar for amplitude. It's like IBP computation. You have a total derivatives here, and it's 0. And it had two contributions. One is when your variation is on the action part. The other is a variation directly on your operator. Okay, there are two contributions. So the derivation is a bit technical, but finally you can set up some rules, which is very nice for programming. And for this action part, we know the action is consistent of just a sum of all plaquettes. So the role of action actually just when you make a variation on one edge, it's actually sew some plaquette on this edge in all possible ways. Okay. And the variation on this loop variable on this operator itself is actually mostly trivial. The only interesting case when you have this overlapping edges. Namely, when you have this edge, original edge here, but after some movement, you come back. Okay. So in this case, it has some non-trivial dynamics for your results. Okay. So this is the example that I show here. The simplest example here for general N would be for a single plaquette. Okay. You get this expression. It's so this. Actually, it's an expecting value for all these loops. This is really a non-productive version for all these values. It's true for arbitrary coupling and for arbitrary N. This is another one. You have overlapping phases. Also, the interesting case is that you need actual complication case. You need to consider some backtrack loops. Okay, this gives you some further equation motions. That's one subtlety. It's an open problem how to generate this kind of equations exclusively when you have a very complicated configurations. So, how many time do I have? Yeah. 25 minutes. Okay, great. I think I have a. So these examples I will show you here. This matrix is what I showed you before. Is a Hermitian positivity conditions. It involves 4 loops. The loops are defined precisely here. And this one is from the reflection positivity. Here I didn't consider the twisted version. Okay, so you get 2 matrices. And These 4 variables are not independent. The version here is the SU2 version in 2D. So we find that these 4 variables satisfy one linear equation. Okay, so it means that only 3 of them are independent. So now you solve this system, right? How to solve this? It's actually a well-known semi-definite programming problems. If you do it in mathematics, there's a so-called semi-definite optimization function. You can do it directly. So this W1 would be the object function. So we know that we want to plot the bounds, right? Which variable, which loop you want to plot the bounds, you have to tell the programming. We want to optimize this W1, the single placket here. And the constraints here are this basically the 2 matrix have to be semi-definite positive, and the variables may be not independent, so you have to auto-impose put all set of equations here. Then this is all variables appear, which is just 4 variables you put here. Okay, so the plus minus give you either upper bound or lower bound. Okay, so when you change the sign here. For this simple system, the mathematical actually works perfectly, but sometimes when it's if you have a size of matrix more than 100 times 100, it would be good to use more advanced tools like the Mosaic, some particular software to solve this kind of linear semi-definite programming problem. So if you solve this 2 matrix, this is actually you see it's 5 times 5. It's actually use 5 paths. So the number of paths is 4. The number of loops variable is 4. Loop equation is 1. So get this upper bound, and the lower bound tells you nothing. Okay. But of course, you can see this matrix is so small. If we increase the matrix, now I use a path, not 5, but 81. You see, the upper bound, there's still little space, but the lower bound is almost coincide with the analytical results. Okay, so in this term, you have 74 loop equations. The independent loop, I think the loop, sorry, this is not independent, but it's just all loop variable shows here, it's 164. So this is the constraints you can have. And in the SU3, here is just a previous result by Kazakov and Zhen. This is a 3D version. You see this is a different size of matrix, but you see from this to blue to red, it has a convergence for 3D. Okay, this is a 4D. Okay, this is I think for the computation is quite time taking. This would be for this dot, you would need 1 gigabyte memory, and each dot would take 20 days. So this is easily to get a time, exhausting your computing resources. Lambda is a coupling, top coupling. Yes. This is a vacuum expansion value of the placket. With loop, this placket with loop, yes. Yeah. No. It's a pure Yang-Mills. Yeah. Yeah, I'm not sure, but for equation motion, it doesn't change. But maybe I have to think about it, because it doesn't contribute to equation motion, the theta term, but probably for these positivity conditions, it will have some effect. Yes. Yeah. This is considered on the lattice. Yeah. Well, actually, this positivity condition, in principle, it applies to the smooth loops. But the problem here, you need to have a finite size matrix. You need to make certain truncation. If you define on the lattice, the loops have a natural truncation by the length of your loops. But in principle, I think if you know another different way of doing truncation, it could be applied to the smooth loops. But this would be the opening question. Here, yeah, actually here when you make a size truncation, you actually don't know the infinite boundary conditions. It means that when you have some fixed you want to detect some phase transition effect, you need to have a long-range interaction, you need to go to large size. But here, so far it doesn't care about that. Yeah, this is also an interesting question. I mean, in real lattice, you have these sign problems, but here the strategy is very different. I think in the Lorentzian case, as long as you can still define this positivity matrix, it should be available in that. It's also another interesting open questions. So let me come back to this SU3 computation. What's the challenging? So as I mentioned before, if you're doing large N, it has a factorization property. So all multi-trace loop can be factorized into single trace loop variables. And in the SU2, all double trace or higher trace can be use this matrix properties reduced to be a pseudo single trace loops. Okay, so finally you only need to deal with single trace loops. However, in the SU3, the best scenario, you can decompose triple trace into double trace. Okay, this double trace cannot be decomposed further. So if you just consider single trace, you see the number of loops increase significantly, very fast when you increase the length of loops. Just to show you an example, the length 4, of course, is only single placket. And the length 6, you also have this length 6 loops. These two are two length 6 loops in 3D. You only have these two configurations. These 7 length 8 loops in 2D would be this 7. Okay. Just show you some examples. Of course, this kind of 4D loops is not visible at all. You have to just do it using the algorithm. Okay, but I think for mathematicians, I think systematic counting and constructing these numbers would be interesting problems. Also, maybe encode the SDE constraints. Yeah. As the swing decimal loop equations. So here, I haven't used the constraint of loop equations, but in principle, you should also. I think for the local operator in EFT, there are some Hilbert scheme methods to use that to count the number of independent operators directly. But I think for this non-local loop variables, it probably is not known yet. So this is just for the single trace loop. You can imagine that when you consider double trace, the number is increasing significantly. So before the study is only for the SU2 or the large N. So a initial question is that does the same strategy works well for the SU3 case? So this is a concrete problem we want to check. So also the SDE would be more complicated in the SU3. You need to consider the Schwinger-Dyson equations for the double trace operators. So this is much more complicated. These are examples I show here. So to deal with these difficulties, we introduce some simplification. One of these to kind of a dimension reduction techniques. For example, if you consider 2D loops, we ask the loops only extended in one direction. Okay, so effectively it's on a one-dimensional strip. Okay, you may ask why you can do this, because the Schwinger-Dyson equations are closed. You can just make a variation on this on this kind of links. So you can develop a closed system for these loops. And also for the 3D, you can actually restrict your full 3D lattice on a 2D sublattice. It will be subplane. Okay. The Schwinger-Dyson is also closed, but you cannot reduce it further. For example, 3D to 1D, because you lose these closed properties. Okay. So if in the 2D case, if you compare the number of this generic loop and this ladder type loops, you see the number of loops is much smaller. Okay. And these are examples of the 3D kind of paths you use to construct the matrix. And also for the 4D case, the number of loop increased so large, you have to use further tricks to make this reduction. Okay. In the remaining time, I will show you basically present the results we have obtained. So this would be the SU3 in 2D version. Okay, so if you consider the number of paths would be 69, the loop equation would be about more than 100. But this is just to let you know what's the size of the matrix you have to solve. The lower bound is almost close to the analytical part. But to reduce the upper bound, you have to increase the number of the paths. The path is the size of the matrix. So this is certainly a truncation when you consider a fixed size of the path. Okay. This is coupling. The axis is a expression value of this the Black-Edwards loop. And this is the part that when you consider the same, this the 69 size path, by only including further, this is a twisted reflection. Okay, that's what you see that the upper bound immediately reach these analytical results. And this is the derivation of the bounds to the analytical results, bound time analytic minus analytical divided by analytical. It's a 3 digits precision. You see. So without the twist condition, it converges much slower. So this in 2D, this is a very, very nice property you can use. Okay. This is the 3D, which is not solvable. You see that the size would be from the 200 to 400, and this would be the more than 1,000. You see there is a clear convergent properties. Okay. All this upper bound and the lower bound can be done on a laptop. So this is a truncation that we make. And okay, if you compare to the 2D, so compared to the SU2, so similar size here would be 500. This would be 800. The bounds would be give you like this. Okay. So I think the lesson we learn here is that even the number of loops increase or contain the double trees, the convergent property still shows here. So the conjecture is that when you increase the number of the paths further, maybe finally it can converge to your lattice results. I think that's a conjecture. And for the 4D, it's much harder. When you increase the dimension further, the number of loops also increases much more significantly. So this would be 500 bounds, 1,000 bounds. This would be I think 6,000 and 3,000 bounds. Okay. And compared to the similar SU2 version, it's comparable, I would say. Okay. So these dots are Monte Carlo simulation. Any questions so far? So I should emphasize these bounds are rigorous as long as you obtain that. It's a necessary condition for your physical quantity. And the further improvement must inside these bounds that you have obtained so far. Okay, this is come to my summary. So I think the bootstrap strategy has played increasingly important roles in various studies. And in this work, we present some new progress for bootstrapping lattice gate theory. We first consider this SU3 involving double trace operators. We show that the strategy still have a clear convergence properties. And the conjecture was that this would be maybe for general SUN. Of course, for higher N, your system would be more complicated, but the convergence property may still works. And we also consider a dimension reduction techniques that reduce your D-dimensional lattice to almost a D-1 subplane. And for 2D, we consider this twisted reflection, which is quite constraining in this case. And for the challenging how to make a good truncation of the loops, this is, I think it's a very crucial problem to make it practically solvable. And how to derive a full set of Schwinger-Dyson equations very efficiently is still, I think it's kind of algorithmic problem. And how to improve this as semi-definite programming is also so far this program is not very good for parallelizing. It's not like a Euro lattice simulation, use a larger number. But estimate semi-definite programming. It means that when you have the positive matrix, you have to solve the bounds. Okay, solve the upper bound and lower bound. This we do numerically using this software. And also, are there any new physical constraints you can impose? As we see, this twisted version is very helpful in 2D. Are there new constraints that you can introduce? And we, in the results, we present only for the single plateaued Wilson loop. How about the larger size of Wilson loops? This is, in principle, this should also applicable. And also for more general theories, in particular QCD with diameter quarks, will be a very interesting theory to look at. Of course, the final goal is that we understand this mass gap and confinement problems. For example, study the area law for the general Wilson loops, as well as Wilson loop correlators to extract the global mass, for example. So I will stop here. Thank you.
Okay, thanks for the interesting talk. Are there any questions?
Oh, here.
Here.
This right line from the string, a strong coupling calculation seems to cross this upper bound, right?
No, yeah. This actually, the behavior of this line depends on the truncation of your series. Actually, if you're including another term, it could be going like here. So yeah, it's a typical this perturbative expansion result it has. It's not a conversion. It can certainly go like this if you're including higher order.
So I should not trust this result? Or?
I think at the strong coupling region, you certainly trust it. But in this region, it's no longer trustable. In a strong coupling would be at which order? I think here, let's record this. Maybe this order you can have a quite large expansion. I think could be the 10th order. Yeah.
Any other questions?
Yes. I think so. For example, for the strong coupling, it's actually quite insensitive with the dimension, actually. At weak coupling, maybe I should mention that actually there is you see what's the difficulty here. From 2D, the curve is quite smooth for 2D. And for the 3D, you see there is a certain transition. And for the 4D, the difference between weak and strong is also getting larger. Actually, the lattice simulation shows that if you go into SU5, there is a first order phase transition here. So this actually gave a very challenging for your bootstrap, because for the bootstrap, you want to have a curve that exactly match your bounds, match your results. There is a first, if you consider finite temperature, when there is a phase transition when going from the 0 temperature finite. Here it's all 0 temperature, but it consider just the expansion of a single Wilson loop. You count I think this is from a different mechanism. Yeah. So sorry. You get nothing bounds at all, almost, because the matrix you always have new variables, new operators encounter. So here, why it's important using the Schrager-Dyson equation, also for SU3, when you so as I said, when you're making Schrager-Dyson equations, you also have this triple trace operators, but all those triple trace operators can be reduced to the lower trace operators. So this is, you have a closed system, and there's a but if you so if your system don't have this equation motion, your elements would be the variables in your matrix would be too large. Yeah, but you also get no bounds at all. This is also important because it will tell you that it's series dependent. If you change your action Lagrangian, you get a different type of Schrödinger equation. In principle, you can get a bound, but of course, in lattice, we know the irreverent operator, when you take the smooth limit, it disappears. But at least at the finite size, it can affect your results.
We have time for any more questions? Okay, if there are no questions now, then let's thank the speaker again.